Okay, every physicist, or everybody who studies physics to a high degree, goes through two existential crises. Welcome to existential crisis number one. We're going to be talking about Einsteinian relativity. And this was a huge fundamental step forward in understanding of the universe when it was actually first proposed. So let's go back in time. Let's go back to Maxwell. And we use Maxwell's equations to this day because Maxwell's equations predict EM waves very, very well. But according to Maxwell and various other people, see, the speed of light equals 2.998 times 10 to the 8 meters per second. In fact, we know this very well. We can measure that to like 11, 12 significant figures. It's one of the most accurate things we can measure. Now, in fact, we used to define how long a meter was by how far light travelled in a certain amount of time. So we know the speed of light very well. But who measures it at 2.988? If I'm standing in a lab, do I measure it at 2.98? Right? What happens if I'm in a car and I'm driving along and you've got the speed of light and then I'm travelling? How do we take this into account? Do I measure it slightly differently because I'm travelling in the same direction or the opposite direction? And according to Maxwell, there used to be something called ether. And ether was what light travelled through, electromagnetic waves travelled through, which, I mean, there used no sound, and sound had to go through air or things, so they said that light and electromagnetic waves travelled through ether, and that we measured everything relative to the ether. And so what they came up with is, if we've got, this is us on Earth, and Earth is going around something called a sun, and sometimes we're going this way, sometimes we're going that way. So therefore, we should be able to measure a change in the speed of light depending which part of the sun we're going around. And they came up with this whole, and a couple of physicists, Michelson and Morley, decided to do an experiment to actually prove that the speed of light is different. Of course, actually what they proved was that the speed of light was the same, so they basically destroyed the concept of ether. Though this still hung around in popular culture for a while, and people like C.S. Lewis, when he was writing his spaceship science fiction stories, used to have ether ships that travelled through the ether. And we still talk about it even nowadays, about how radio waves, the message came through the ether, through the radio waves. But, so, this whole concept with the ether was wrong. So, but then along, in 1905, somebody working as a patent clerk, a young guy called Einstein, came up with a different way of looking at things. And Einstein came up with general relativity and later on special relativity. We'll really be just focusing on special relativity. If you want to look into general relativity to any degrees, Waikato University does offer a master's course through the mathematics department in general relativity. But he came up with a couple of postulates. Any good theory should have your basic postulates, your basic assumptions, and you should say what they are at the beginning. So basically he says that the laws of physics are the same in all inertial frames. And so basically, if you're not accelerating, then laws of physics should be the same for everybody. Doesn't matter whether you're on Earth or Alpha Centauri, you're out in the Andromeda Galaxy, or the laws of physics should be the same as long as you're not accelerating. And his other one was the speed of light is the same for all observers. All observers. And what that means is if I'm sitting here and a photon of light goes past, whee, I measure that at approximately 3 times 10 to the 8 meters per second. If I'm driving along and a photon of light zips past, I also measure that at 3 times 10 to the 8 meters per second. So it doesn't matter how fast you're going, light is always travelling 3 times 10 to the 8 meters per second relative to you. So let's actually try this in an exercise. So let's do exercise, what's the 7.1 we're up to now, isn't it? So basically observer A observes a pulse of light to travel past at the speed of, okay, so we've got observer A, so this is basically, I'm standing there and we've got light going whee past, and I measure that at 3 times 10 to the 8 meters per second. Isn't that cool? But now we stick observer B, so this is A. Observer B is in a rocket ship, and observer B is travelling at 1 times 10 to the 8 meters per second. Cool. And the speed of light, the light is travelling at 3 times 10 to the 8 meters per second. So according to the classic stuff that we've been doing earlier, remember what we were saying before about velocities and things like that, is that the velocity of OG equals velocity of, I should go and look this equation up. Doing this just before, so it's inertial frame, that's equals the velocity of the observer to the system plus the velocity of the system to the ground. Remember that? So what this means is, this was the tree stuff, so if I have the tree there and I'm walking towards the tree, somebody's cycling towards the tree, remember all that stuff? So basically what this says is I can rearrange this so the speed of light should be relative, I can measure that relative to the speed of the van to the ground. So I can rearrange this velocity, so the speed of light to me in the van is equal to velocity relative to the ground minus the velocity of the van. So that's equal to 3 times 10 to the 8 meters per second minus 1 times 10 to the 8 meters per second, because that's how much. So according to the classic Galilean reference system, it should equal 2 times 10 to the 8 meters per second. But according to Einstein, it says the person in the van should be seeing the light travelling at 3 times 10 to the 8 meters per second. You'll notice that now there's an instant disparity. So this is the classic Galilean stuff. This is what Einstein's saying. So which of those is right? And from experimentation, we have actually shown this one is right. That means the Galilean one is not right. Yet you'll notice in reality 99% of the time we'll use the Galilean reference. So I will use that when it's wrong. And the thing is, as long as you're talking low speeds, it's fine. I mean, if you're talking speeds less than a 10th, 20th of the speed of light, then usually the uncertainty provided is less than the uncertainty of the actual measurement. So, but the big thing here is when you get approaching the speed of light, Galilean physics breaks down, Galilean relativity, and we need a new form of relativity. So we have to use Einsteinian relativity.